Hello everyone, this is Abhishek here. Today I'm I'm going to discuss regarding rotor earth fault detector. So I've chosen a MICOM 391 rotor earth fault detector, and this is the internal equivalent circuit. So it consists of a V injection source and which has a source resistance of R source, and this is the R return wiring resistance. R measure is a known value of resistance, and these two are resistance, these are also known values. C by 2, this is the capacitance of the rotor field related to ground. So, since it is a lump parameter model, we have lump all the capacitance equally at the ends, right? R fault resistance is infinite. We have assumed that there is no rotor earth fault initially, right? So, these currents are returning via earthing brush back to the network. Now, initially, since there is no rotor earth fault, the rotor voltage will circulate a current in this loop. And at the positive half of the V injection source square wave, the orange color lines indicate the capacitive charging current for the positive half. So using Kirchhoff's voltage law, uh, you can see that this 2R and 2R resistance will be parallelly uh, added up, and this capacitance will be added up like this: C by 2 plus C by 2 equal to C. Very simple, just KVL, just apply KVL, you'll get to know. And since these currents are passing through a very small time constant network, so they will be very steeper in nature, and they won't have significant amount of AC in it, right? So it is of no use. But whenever there is a fault, there will be an offset current. There will be current which will pass through this fault resistance via the earthing brush back to the network, and this capacitive currents will also exist at the same time. So there are three components of current: this one, this one. Remember, these two currents are through the capacitance of the field with relative to ground, and this one is through the fault, and it will finally return through the shaft and come out through the earthing brush to the detector. Two wires go into the earthing brush. One is for earthing and another to the detector. Fine. But this current path will return through the nearby earthing strip. If I assume it to be a TNC combined system, TNCS combined, and I think it is pen conductor, right? TNCS combined and separate. Fine. So whenever there is a fault resistance, what will happen? There will be a current component which will be an offset, and it will raise the total waveform of this fault current. This voltage drop will balance this one, this voltage drop and this voltage drop. The fault can occur at any location, at any point. I have shown it in the middle, but it may occur here, it may occur here, it may occur anywhere. But the first rotor earth fault, we are considering the first rotor earth fault, right? The analysis becomes different whenever there is a second rotor earth fault developing. So let's see the waveforms now. Let me just switch off the camera, right? So now this is a V injection source, square wave, positive and negative halves. So by Fourier analysis, you can find that the fundamental component is 4 into V injection by 3 pi. And this is the fault current when there is no rotor earth fault. And this is the fault current whenever there is a rotor earth fault. There is an offset, as I've already told you, and the fundamental component can be calculated by using this formula. But what is I fault here? That needs to be known. I fault is equal to, what we have done is, since this capacitive effect is active for a short time, we have taken this component, and this component. These two components subtracted divided by 2 will give this amplitude. So this amplitude, when I use it in the Fourier expression, this becomes 4a by 3 pi, 4I fault by 3 pi. This is a fundamental component. So this can be used in the network, a simplified network. This is a simplified network. R coupling, as I've already told, is R. R fault is to be calculated. This one is known. This one is known. This one is also known. V injection will take the fundamental component of the square wave, and I fault is already known, fundamental component. So when I divide these two, I'll get the total resistance. From this total resistance, subtract all the known values, I'll get R fault, which can be displayed on the LCD. Now, I fault is known to me, R measured is also known to me. The product gives me V measured. So V measured can be used for some sort of relay pickup, etc. Right. So that much only, very simple analysis of rotor earth fault. But just remember that this analysis is active, is valid in fact for a first rotor earth fault. For second rotor earth fault analysis, it becomes very different. In fact, we need not wait for second rotor earth fault to develop. The first rotor earth fault automatically will ensure the tripping signal is uh, reaches the proper target. So these are some diagrams of the hydrogenerator, hydrogenerator aspects related to the excitation system, in fact. And this is the smooth sleeve rings, collector rings with brush rocker, carbon brush, groove sleeve rings. And this is the brush rocker close-in view. This is the complete assembly of the field poles. This one is the individual field pole. Whenever there is a rotor earth fault, this is a structure without field poles installed. So whenever there is a fault, rotor earth fault, the fault current will pass through this metallic structure to the shaft and go down, and finally will come out via the grounding brush. Right. There are two wires normally connected here. One is for grounding, another to the detector. So that current will go to the detector, as I've already shown in the first diagram, first slide. So it goes to the is a return current to the network, back to the network. So that much only. Hope the video was useful to you. Thanks for watching.